The next little bit, we're going to talk about the derivatives of the inverse trig functions. Remember, we had sine and arcsine, and cosecant and arccosecant. So in section 5.1, you saw the derivative of a transcendental function. F of x is the natural log of x, is an algebraic function. So we derived a transcendental, and we got an algebraic, 1 over x. You will now see that the derivatives of the inverse trig functions are also algebraic, even though the inverse trig functions themselves are transcendentals. So the following theorem lists the derivatives of the 6 inverse trig functions. Proofs for the arcsine of u and arccos of u are shown in Appendix A. The rest are left as an exercise in the book. Note that the derivatives of the arccos, arccotan, and arccosecant are the negatives of the derivatives of arcsine, arctan, and arcsecant. And that's easy to see here in the theorem box 516. If you look at arcsine and arccosine, they are exactly the same except for this negative. The same between arctan and arccotan. They are identical except for a negative sign. And if we take arcsecant and negate that, we get arccosecant. So let's take a look at these. The first one, the arcsine of some function u, if it's a composite function, anything more complicated than just x, its derivative, the derivative of it, we're going to take whatever this u is and put its derivative up top. That'll be u prime. And then in the denominator, we have a radical, 1 minus whatever this u value is. Again, we square it. 1 minus u squared under the radical. Again, negate that to get arccos. Now let's look at the difference between arcsine and arctan. We see the radical is gone from the denominator, and this minus sign is now a plus. So it becomes 1 plus u squared in the denominator, no radical. Numerator is still u prime. Again, negate that to get arccotan. And the last one, arcsecant. If we look at the original arcsine, the numerator stays the same, it's just u prime. What was under the radical now, that square root of 1 minus u squared, we've flipped it. Now it's u squared minus 1 under the radical. And out in front of the radical, there's something completely new, an absolute value of u. Again, that's arcsecant. Negate that to get arccosecant. These look pretty complicated. These are something you're just going to have to memorize too. There will be a little quiz on these derivatives of the inverse trig functions, but actually applying them isn't overly difficult. You'll see what I mean here in example A. So we're going to take the derivative of these inverse trig functions. The first one is the arcsine of 2x. The first thing I like to do is identify u, whatever the u value is here from the formula, and that's just what we're taking the arcsine of. So here, u equals 2x. So now we're just going to plug the relevant parts into our formula, and this is u prime over the square root of 1 minus u squared. So let's plug some stuff in. The numerator is u prime. If u is 2x, u prime is 2. Underneath the radical, we have 1 minus u squared, whatever u is. And for us, our u was 2x. So I'm going to work down this way a little bit. Numerator is still 2. Underneath that radical, we have 1 minus. This was the quantity 2x squared, or 2x times 2x, and that is 4x squared. And that is about as simplified as we can get it. There is our derivative of the arcsine of 2x. Okay, let's take a peek here at letter B. Now we're on to the arctan of some quantity. And I'm going to put the formula right here under it. That's u prime over 1 plus u squared. So again, we got to figure out what u is. And here it's a nice easy one. U is equal to 3x. So our numerator is u prime. The derivative of 3x is 3. And then in our denominator, we just have a 1 plus whatever u is, quantity squared. Again, that was 3x. So we can simplify that 3x quantity squared and make it 9x squared. So there's our derivative of the arctan of 3x. Okay, looks like this is going to be a little trickier here for letter C. It's another arcsine, so that's going to be u prime over 1 minus u squared all square rooted there. So let's see here. Our u is the square root of x, or x to the 1/2. So u prime, the derivative of that is 1 over 2 square roots of x. So now let's plug that into the proper spot. This u prime is our numerator, so we have a 1 over 2 square root x is our numerator. And then our denominator is under a radical, 1 minus whatever u was, quantity squared. And our u again was square root of x. So let's see here. We'll leave that numerator alone for now. 1 over 2 square root of x. And then underneath this radical, the square root of x quantity squared is just plain old x. So down here we now have a 1 minus x. And it is kind of bad manners to leave fractions within fractions. So this fraction up top, we can sort of drag it down front, and we could sort of write it as 1 over 2 square roots of x times 1 over the square root of 1 minus x. And then we can multiply straight across. We'll have a 1 in our numerator. We'll have a 2 times the square root of x times the square root of 1 minus x. And I guess if you left it that way, that's not too bad. If this was a homework problem and you were comparing to the back of the book would take it just a little bit farther, and they'd get combine these terms here together. Sort of since they're both under radicals and we're multiplying, we can put them under one radical and distribute the x across that second binomial term. So we'd have a 1 in the numerator, 2 in the denominator, and then we'd have our radical. X times 1 is x. X times x is x squared. And there we go. Okay, last one, letter D. Ooh, now we have an exponential. Oops. E to the 2x. So, this is arcsecant. This is, I think, one of the more complicated formulas, because we got our u prime up top, and then in our denominator we have an absolute value of u, and then times the quantity square root u squared minus 1. So let's see what happens here. Our u is e to the 2x, and our u prime, the derivative of e to the u is e to the u, e to the same 2x, and then we got to multiply by u prime by the chain rule. And our u is 2x, so that derivative would be 2. So 2 e to the 2x is our u prime here. So let's see what happens. Our numerator is u prime. That's 2e to the 2x power. And all over, let's see, down here we have the absolute value of u, or the absolute value of e to the 2x. Are the absolute value bars necessary? Remember the exponential, all exponentials across at 0, 1 and go up. Does it ever go below the x-axis? Are the y values ever negative for an exponential? No. So the absolute value bars, if you did leave them there, I wouldn't mark it wrong, of course, but they're unnecessary because of the nature of that exponential function. And then we have our radical. Underneath the radical, we have u squared, e to the 2x squared. What is e to the 2x times e to the 2x? Well, multiply like bases, add exponents. 2x plus 2x is 4x. E to the 4x minus 1. And it is nice here too, since we are dealing with the exponential, this e to the 2x and this e to the 2x in the numerator and denominator will cancel. And that just leaves us a 2 in the numerator and then our radical in the denominator. E to the 4x minus 1. Okay, I think there is one more example in this section. A derivative that can be simplified. Ooh. If it can be simplified, that means it's going to get a little complicated to begin with. So let's see what we have here. Our function is the arc sine of x. We can take that derivative, no problem. And then here we have one function x times this function, the square root of 1 minus x squared. So this is going to be a product rule that we're going to have going on here. That looks like it's going to be the sticky part of this problem. So let's see here. The derivative of x is 1, And in the quantity, that radical, we have 1 minus x squared to the half power. So when we take that derivative, it's going to be 1/2 times that same quantity to 1 power lower. Now it's the negative a half power. And then the chain rule says derive the inner function. So within the parentheses, that function's derivative is, don't forget the negative 2x. And let's see here, the 1/2 and the negative 2x is just going to combine to negative x, and then our quantity, 1 minus x squared to the half power. And that's supposed to be a negative half power there. So I guess we could rewrite it as, we'll take that quantity to the negative half power and move it to the denominator. So negative x over, and let's even write it as a radical, why not? 1 minus x squared. 1 minus x squared underneath that radical. Okay, and that was just, all we did was find our derivative set up for the product rule, so I'll get rid of that scratch work there. Our function is y equals, so we're looking for y prime. And the derivative of arc sine of x. And here, u is just equal x, so we can just go right by the formula. The derivative of the arc sine is going to be 1 over square root, 1 minus x squared. So that's the derivative of the arc sine part. And now plus, now we need the product rule. So the first function is x times this derivative here in red that I'm just outlining in black. So first times the derivative of the second, if we multiply sort of on that diagonal, we'll get negative x squared over that denominator. Negative x squared over our 1 minus x squared under the radical denominator. So that was the first times the derivative of the second, plus the second times the derivative of the first. So our radical 1 minus x squared times 1. So that's just going to be plus 1 minus x squared. And because the directions did say a derivative that can be simplified, I'm going to put this over a 1 just to remind myself I have 3 fractions here. So let's see. The first 2 fractions have a common denominator. Radical 1 minus x squared for the first 2 terms. Here we had that term, but it's in the numerator. Our denominator here is 1. So let's multiply the numerator and denominator of this last term by radical 1 minus x squared. So let me rewrite the first 2 terms here. 1 minus x squared. And we can change that plus. I guess this plus is overpowered by this negative sign. Minus x squared over radical 1 minus x squared. Plus, here now we have our denominator, 1 minus x squared under the radical. And in the numerator, radical 1 minus x squared times itself is, we just wipe out the radical sign. Now it's 1 minus x squared, and that almost looks like a 3. There we go. Now all the denominators match, so we can just, add or subtract the numerators as the problem dictates. So let's see here. We're going to have a big divider line, 1 common denominator, 1 minus x squared under the radical. And our numerator here, we have a 1 minus this middle x squared plus 1 minus x squared. And if we combine all those terms in the numerator, get this out of the way. So we have a 1 and a 1 is a 2 minus x squared is 2x squared over our common denominator. Let's see here. If you left it like that, I'd be happy with that, or should try to get that radical out of the denominator. But there is a neat little trick to this, and given by, we can simplify it. Let's factor a 2 out of that numerator. 2, and then we have 1 minus x squared. That denominator, it's in radical form. Let's write it as a rational exponent. 1 minus x squared to the half power. Is there an exponent with this numerator piece? Of course, there's a 1 there. So now we have the same quantity in the parentheses with different exponents that we're dividing. What if I had x to the 7th divided by x to the 5th? Well, that would be x, and the power would be numerator exponent minus denominator. 7 minus 5 is 2. So that would be x squared. We can do the same thing here. Our final answer is going to have a 2. And then we are going to have this quantity, 1 minus x squared. Oops. And let's check our exponents. 1 minus 1/2 is 1/2. So there's our final answer. You know, here it looked pretty complicated to begin with, the arcsine of x, plus, and then we had our product rule going on here. When it was all said and done, it did simplify down real nice to 2 times the square root of 1 minus x squared. So just to review here the rules, in the 1600s, Europe was ushered into the scientific age by such great thinkers as Descartes, Galileo, Huygens, Newton, and Kepler. These men believed that nature is governed by basic laws, laws that can, for the most part, be written in terms of mathematical equations. One of the most influential publications of the period, Dialogue on the Great World Systems by Galileo Galilei, has become a classic description of modern scientific thought. As mathematics developed during the past few hundred years, a small number of elementary functions have proven sufficient for modeling most phenomena in physics, chemistry, biology, engineering, economics, and a variety of other fields. An elementary function is a function from the following list, or one that can be formed as the sum, product, quotient, or composition of functions in this list. So here's our algebraic functions, simple polynomials, rational functions, functions with radicals. And then we have our transcendentals, the non-algebraic, the log functions, the exponentials, the trigonometric, the inverse trigonometric functions. With the differentiation rules introduced so far in this text, you can differentiate any elementary function. For convenience, the differentiation rules are summarized here. So all the way back to our constant multiple rule, sums or differences. Here's our product rule, the power rule, derivative of a constant, the quotient rule, the natural log function, log base a, e to the u. Here's our sine and cosine and tan functions. Now we add to these our new inverse trig functions, and here we now have 24 basic rules for the differentiation of elementary functions. You know, these are things you are going to have to memorize and know forward and backward, especially for that AP test. Enjoy.